Okay, so let's move on to our challenge 3, which says make urandom and get random collide, which means that we need to somehow hijack these system calls where these functions are being called and manipulate some logic in order to make these functions return same value. So let's see, open up our binary again in Radare 2 and analyze it using AAA. Let's list down the function using AFL and go to our challenge 3, which is at this offset. So let's move our cursor to E8C and now let's see the disassembly using PDF command. So here in the disassembly, we can see that it's opening a file using open system call and the argument or the path pointer is /dev/urandom. Then it's reading a file using read system call and the read system call takes three argument, file descriptor, buffer and number of bytes which needs to be read. So all these three arguments are listed here. So this is the file descriptor, then it's reading 20 bytes into this buffer, right? Similarly, in the next segment, again we have the read function call, and this time it's taking this buffer as a file descriptor and reading only 1 byte, okay? So at this point, we can say that it's reading first 20 bytes from this file, and after that, it's reading the single byte, the first byte actually from this file. Then moving on, some comparison which are being made. So let's try to understand it better by looking at its decompiled code using PDG. This will give us much more better idea what's going on. So it's open the file and the file descriptor has been stored in this variable. Then it's reading the first 20 bytes of this file and first byte from this file again. And these values are being stored at these variables AC stack 72 and AC stack 80. And then it's closing the file. Then we have our get random function call. Let's see what the get random function call looks like. So get random. Again, we are going to look at its Linux manual. So it returns the size and it takes three arguments: buffer pointer, buffer length, and flags. Okay, so this is actually the size. So we are reading 20 bytes from this buffer. Now what this buffer is, we don't know. So we can use register read method of Qiling API in order to figure out the address where this variable is present in the memory, and this way we will come to know what's being written into this variable. Then we have this for loop, and inside this, so basically this is the counter, we can say. No, this is just some checker. So it's initialized with 0 and it's being increment here inside the if condition. So if this if condition becomes true, then it will basically increase this counter, and if it matches to 0x20, then our challenge will be solved. Let's try to figure out what's going on in this for loop. For that, this iStack88 is actually our for loop counter, which is being incremented here. And if this is less than 20 bytes, then till 20 bytes it will iterate, and it's iterating over AC stack 72, which is the first 20 bytes of this urandom file. So if the first 20 bytes of this urandom file is equal to AC stack 40. Okay, makes sense. So if the first 20 bytes of this urandom is equal to first 20 bytes returned by this get random function, then this condition will be true, and AC stack 72, which means again the first 20 bytes of urandom, this should not be equal to AC stack 80 0. Okay, so the first byte of, or basically the all bytes of this urandom should not match the first byte. Okay, so now we have understood what the logic is. So all we need to do now is to make sure that the bytes written by the get random function matches the bytes written by this read function, and the first byte of this urandom file should never be equal to the first 20 bytes of the same file. So logically we know that this condition will never becomes true because getRandom function will never return the same bytes which is present in this dev urandom file, right? One way to solve this challenge is by hooking the read function and modifying the bytes inside this buffer, right? Similarly, we need to again hook the read function and modify the bytes in this buffer so that they will never be equal. And we need to hook this system call getRandom and make sure that whatever the bytes we have written into this buffer, the same byte should be written into this buffer. That way this condition will become true and we will solve the challenge. So now let's go back to our script and create a function to solve our challenge 3 QL. Now we have already seen in order to hook system call, we can use ql.os.set underscore syscall, and this takes three arguments. First one is the name of the function, which is read function, and then we need to create a callback handler. So challenge 3 read callback, and the second argument is args. Then we can pass this callback here, and then we can tell when to trigger this system call, whether at the time of enter or exit. We can use the exit here because at the time of exit we need to modify the buffers. Typo here, sorry for that. Okay, and similarly another we need to set up another hook for get random function, right? And let's create another callback handler. Let's say challenge 3 get random callback ql comma pointer args. This will be triggered when get random function will be called. Okay, now let's define the logic for these callbacks. So first of all, when the read function is called, we need to modify this buffer and also this buffer. So one way to differentiate between these two reads is by looking at the size. So what we can do is first we need to resolve the parameters. So again, I am going to store the params into this params variable, then ql.os.resolve for f call params function to resolve the arguments for read function. So as I already mentioned in Qiling framework, we don't need to bother about the internal implementation, how the functions are stored, whether it's on stack or in registers, and how to handle it. So this function will do the job for us, and we just need to tell this function about the type of the arguments and number of arguments. So for read function, first argument is the file descriptor, which is of type integer. Then the second argument is our buffer, which is of type pointer. Then the third argument is our size, which is of type integer again. And we need to import this integer constant just like we did with the pointer using killing.os.constant. So here I am just going to import it. Now our parameters for this read function have been resolved. So what we can do now is we can simply check if params, if the size of the read function is equal to hex 20, but here we are interpreting it as int. So the integer equivalent of hex 20 is 32. Now if the size of read function is 32, then we need to get the buffer, which let's say we are going to store into bytes 20 variable, and using ql dot now we need to get this buffer, right? So this buffer is already there inside this buff field, so we can simply do bytes underscore 20 and read the buffer from our params variable. Okay, so now we have this buffer into this bytes 20 variable. Okay, first of all, let's see what's there inside this buffer. So before modifying bytes 20, we have ql.mem.read bytes 20, and this is for 20 bytes, so let's read 20 bytes. Let's comment this function and this function for now and call our challenge 3 just to see what's there in this bytes 20. Let's try to run it. So before modifying bytes 20, it's start. So now what we can do, we can simply write some bytes into this bytes 20 buffer. So we know in order to write data into the buffer or memory address, we have this write method of killing memory API, which we can call using ql.mem.write. And the first argument would be our bytes 20, and the second argument would be our data. So let's write, let's say ff. Okay, this can be any arbitrary byte, whichever you like. I am going to put ff. So the first 20 bytes of this file will always be ffffff, right? Let's see whether it's working or not. So let's print the bytes after modification and see what do we get. So before modifying we have start, and after modifying again we have start, but the first byte is actually replaced, so we need to replace this ff till 20 times. So we can do that using into 32, right? And if we run it again, we have ffff all the way till 20 bytes. Same thing we can do. So if params size is 1, then let's store the first byte into this bytes 1 variable and the buffer we have in this params JSON object. So now we get our first byte in this variable, and similarly let's do the same thing. Let's modify this first byte and print what do we have here in the first byte. So it's just 1. We can simply type 1. Yeah, change the variable name here as well in the memory write API. So now we need to make sure that the first byte will never be equal to the first 20 bytes, right? So obviously first let's remove into 32 times. So if we leave it as it is, then our second condition, which is this condition, will be false. So let's put some other bytes here. I'm going to put the, you can put any other byte here, whichever you like. Now let's see what do we get. Earlier it was C, and after modifying we have AA as the first byte. All right. Okay, so now our second condition, which is this one, is true, but still in order to make this condition true, we need to modify this buffer and replace the bytes with ff, similar to what we did here. Now let's uncomment this, and inside this get random we can take our 20 bytes again, because here it's reading 20 bytes. And similar to this one, we can resolve the parameters of this function, and this function takes buffer pointer, size and flag. We are just interested in the two arguments, the buffer and the size, so let's use these two only. And our 20 bytes would be now inside this params JSON object, which we can access using params and index it using the buff key. So if we print it, we should get our 20 bytes which are being returned by get random. Let's uncomment this syscall bytes 20 modifying just to differentiate between the previous and this one. Let's try to run it. Before modifying random, we have okay. Need to read for 32 bytes. Now we have this. Okay, so now all we need to do is replace these bytes with FFFFF, which we can do just like this, and we can print our statement like this. After modifying the random bytes, okay, let's run the script again. And now after random bytes being modified, we got FFFF and our condition is true now. So we got our challenge 3 as solved. Moving on to challenge 4, which says enter inside the forbidden loop. Okay, so coming back to our Radare terminal, we can simply list down the function using AFL command. And then let's try to find our challenge 4 function. And it's present here at this offset. So let's seek to this offset using S. Now we can view the disassembly using PDF command. So here in the disassembly we can guess a few things like we have this loop which is going on. Let's also try to see the decompiled view of this disassembly using PDG. And here we have our loop. By default, the condition of this for loop will never be true because our iStack4 variable is initialized with 0 and the condition says iStack4 should be less than 0, which is not the case. So all we need to do is to make this condition true so that it will come inside this for loop and our flag will be set to 1, which will solve the challenge. Now let's try to see in the disassembly where this comparison is being made. So in the disassembly we can see that there is this comparison instruction which is comparing these two registers, and after comparison if the result is less than, then it will go back to FC0, which is this block, otherwise it will come out of the for loop and return. So in the disassembly there is only this comparison instruction, so we don't need to bother about rest of the instructions as of now. Let's quickly perform a hook at this instruction and try to intercept the values of these two registers, which we can guess from the disassembly that it's going to be 0 and 0. Let's quickly go back to our script and define a new function for challenge 4. Now in order to hook at this specific address, we have ql.hook_address API, and this API takes two arguments. First argument is the callback handler as usual, so we can define our callback here. Challenge 4 callback, and we can pass our killing object as argument here. So this will be the first argument. Then the second argument is our hook address. Now the address at which we want to perform the hook is FE0, but this is the offset, not the actual address when the binary will be loaded in the memory during runtime. So we can't simply put any static address here. So we first need to find out the base address at which the binary is loaded by our loader, and then we can add this offset to that base address. Also note that this loader is not the operating system's loader because we are not actually running the binary. This is the Qiling loader which is used by Qiling Framework to emulate the binary. So let's go to the top and define our base address here so that we can use this base address in other functions as well if required. We can get the base address using ql.mam.get_lib_base, and this will take one argument, that is the path of the binary, which we can again get using ql.path. So this Qiling API will return us the base address of this binary. So now our hooking address is going to be base address plus our offset, which is 0xFE0. And let's pass this as our second argument. Now whenever this hook address will be executed by Qiling Framework, our challenge 4 callback will be triggered. Next we need to define this challenge 4 callback. So for now we are just going to print out the register values. We know that in order to access any register value, we have ql.arg.register API. So by using ql.arg.reg.x0, we can access the x0 register. Similarly, by using ql.arg.reg.x1, we can access our x1 register. Now let's call this challenge 4 at the end and execute our script again. And now we can see that the value of these two registers are 0 and 0, right? Coming back to the disassembly in our Radare terminal, by the nature of comparison instruction, we can say that this W0 is our 0 here, and this W1 will contain the iStack4 variable. So now we can solve this challenge in two ways, either by modifying the value of x1 or w1 register, which is our iStack4 variable, uh, and make it less than 0 so that the condition will be true, or we can either modify this w0 register which contains 0 and make it greater than 0. For now, let's modify this w0 register and make it 1. So in the script using ql.arg.regs.x0 register, set it to 1. We should be able to solve this challenge. So let's run the script again and see whether the challenge is solved or not. And yes, our challenge 4 is now solved. Next we have challenge 5, and in the description it says guess every call to rand function. Coming back to the Radare terminal, we can see in our listed functions that we have challenge 5 at this offset. So using s command, we can seek to this offset. Then using pdf, we can see the disassembly. In the disassemble code, we can see that some of the system functions are being called here. First one is this srand function, and then this rand function. After this, we have some comparison instructions, but as of now, it's not clear what we are supposed to do. So as per the description, we can assume that we need to figure out every return value returned by this rand function. So in order to better understand the logic, let's see the decompiled code using pdg. Here we can see that for loop is running and the result of rand function is being stored in this ivar variable, and then this ivar1 variable is being stored into the stack variable here. So from the decompiled code we can say that this AI stack 32 is an array which is defined here at the top, and the size of this array is 6. So basically whenever this random function will be called, the result of the random function will be stored into this array, AI stack array variable. After that we have a variable initialized with 0, and if this variable turns out to be greater than 4, then it will set this flag to 1 and our challenge will be solved. Otherwise we have another condition here. If AI stack 56, which is this, is not equal to AI stack 32, which is our previous stack where all the values returned by random function is being stored, then it will mark our flag to false, and then it will go to this address which is here, where it's throwing stack check fail exception. So this is our do while loop which is being running, and with every iteration this iStack60 variable is being incremented. So at some point of time we need to make sure that this iStack60 variable will reach greater than 4. And in order to do so, we somehow make this if statement false every time. So we just need to make sure that both of these stack variable contain same values all the time. So this condition will never met, and after fourth iteration it will come inside this if block and our challenge will be solved. And one more thing to note here is that this AI stack 56 variable is being initialized with 0 always here. So the easiest way to make the values inside these arrays same is by hooking this random function and make it return 0 always. So let's quickly hijack this random function using our Qiling API. So coming back to our script, let's define our challenge 5 function. And in order to hijack function call, we have ql.set_API. So this set API is similar to our set_syscall API, and this also takes 3 arguments. And here the third argument is optional. So by default, if we don't pass third argument here, then it will be considered as ql_intercept.call. So the first argument is going to be the function name, which is rand function. Then we need our callback handler. So let's quickly define it here. This we can pass as second argument. And because we want to modify the return value, we need to pass third argument as ql_intercept.exit so that it will be triggered when the random function is about to exit. Then here in our callback handler, we know that in ARM64 architecture, X0 register will always hold the return value after the function is being executed. So using ql.arc.register.x0 and set it to 0 always. This way random function will always return 0. And now let's quickly call this challenge 5 function here. Going back to the terminal and let's execute the script. Killing object has no attribute set_API. Okay, so here actually set_API is part of ql.os. So let's test it again. Alright, so we didn't get any error this time, but in the terminal still we cannot see the result of our challenge 5. So don't worry. At this point we can assume that we have solved challenge 5, and we will try to fix this issue in the next video. And just to give you a hint, we are not able to see rest of the challenge status because of challenge 6, which says avoid the infinite loop. So don't forget to subscribe to the channel, and I will see you in the next video.